sheet with divided it into two parts, the gravitational part that is only an action for h mu nu, and the matter part that is action for h mu nu and the matter field. And we discussed the matter action. We found what are the rules to construct the action. The general rule was that we want to construct something that has reparametrization invariance or diffeomorphism invariance as a gauge symmetry. So that was a low-cost symmetry. That the action had to obey, and if that is the case, it would be guaranteed to get a consistent equation of motion. So that was the idea. But we haven't discussed the gravitational part, so that's what we are going to do today. So what are the conditions on this gravitational action? One is that it should also be invariant under these transformations. So it should be reparametrization invariant. And then the second condition is that if I linearize a linear order, it should reduce to what we already had before in the linearized theory. So we constructed some linearized theory for spin 2 gravity. There was a quadratic action that would give us that linearized theory. So whatever I write here at the quadratic level should reproduce that. So that would look like 1/2 integral d for x, and then we introduce this operator epsilon. That was basically, it was some second order differential operator. For instance, it contained a term which is delta Fox, the D'Alembert and delta mu alpha, delta nu beta, and then there will be others. So we want to construct something that satisfies these two conditions, and that something is called the Einstein-Hilbert action. It's again made of the metric and its derivatives. So we also saw that in the construction of the matter action that h mu nu never appears by itself. It always comes together with the Minkowski metric in one combination, which is so this h mu nu, it always appears inside the metric, which is eta mu nu plus h mu nu, and this matrix, which is called the metric, that transformed like a tensor on the general coordinate transformations, while neither eta nor h transform like tensors. Okay, so this Einstein-Hilbert action is also is also constructed out of g mu nu and its derivative, and it's given by this integral. So this is at the moment this is just a name R. It's called Ricci scalar. But it's some object, some scalar. So R is some scalar quantity that is related to the metric and its derivative. So in total, this has two derivatives. And then it's a full nonlinear function of h mu nu. If I want to expand it, it's a full nonlinear function of h mu nu with only two derivatives. So for instance, it is so it has two derivatives, and then any number of h's. It can be 1h, 2h, so on. write the exact form because it's written in the note. But at the current level, it's just some nonlinear object that satisfies these two constraints, which are the only conditions that it has to satisfy. Later on, we see that this R has a meaning. When we talk about manifolds and curvature, then we can relate this R Ricci scalar is related to the Riemann tensor, curvature tensor, and then we see that it also has a geometric mean. Now, if I derive the equation of motion from this action, if you remember, we defined a stress energy tensor in the previous section by varying the matter action with respect to the metric. So it would be the variation of the matter action with respect to G mu nu, and we said that this has the property that the covariant derivative of T mu nu is zero. It is covariant, the concept. And we said that we can think of this T mu nu as, so if you remember, we were talking about constructing order by order this nonlinear theory of gravity. So there will be a zeroth order contribution from the matter fields, and then once we add that, once we write the equation of motion, there will be, we have to complete it as nonlinear order. So just putting T0 in the equation of motion for H mu nu, that would be inconsistent. We had to add higher order terms. And he said that in principle, one could just try to do this exercise order by order, and there will be terms at many orders. So this T mu nu that we constructed here should be thought of as the summation of all of these things. All of these stress energy, matter stress energy tensors at different orders in H mu nu. So it's a fully nonlinear object in H mu nu with the property that if I set H mu nu to 0, it reduces to the matter, to the original matter stress energy tensor. And in fact, that's gives us one nice and simple way of deriving a stress energy tensor even in the absence of gravity. We can momentarily introduce some metric in the theory, make it covariant, do the variation with respect to that metric, and then set metric back to eta linear. Okay, so now we should do the same thing. Let's look at the variation of the Einstein-Hilbert action. So 2 over square root of G delta Einstein-Hilbert G mu nu. So that gives us, I might be missing minus sign somewhere here. So do you have the notes? Is there a minus sign here?
Yes.
Here, right?
16.
Oh. Okay. Yeah, now it makes sense. Okay, so if I do variation of this, what we get is something that I call it big G mu nu is called the Einstein tensor. So if I put them put these two terms together, so the variation of the total action with respect to G mu nu, if I multiply by 2 over the square root of minus G, that gives me minus 1 over 8 pi G mu nu plus T mu nu, and that has to be 0 on shell. So that gives the Einstein equation.
I'm sorry, how did you get that? I mean, what is that G mu nu?
At the moment, I just defined it to be this.
Okay.
I haven't said what is G mu nu. It's just a variation of this action with respect to little g, variation of this action with respect to the measure. I haven't even said what is R, but it's not unknown. It is known. It's some linear function made of metric and its derivatives. I mean, I can write it here, but I don't think it's very illuminating to write it. But yeah, this is a function of the metric and its derivative. And once you have an action which is made of G mu nu and its derivatives, we can do the variation in the usual way. And we get some tensor. Since we are doing variation with respect to a tensor, we are going to get as a result another tensor.
Okay.
And then if we vary the full action, we are going to get T mu nu from here and that other object from there, and that would be the equation of motion for the mesh. Now, one property that this G mu nu has is that since by construction this Einstein-Hilbert action at second order reduces to what second order action that we constructed before, then what it implies is that if I look at this, if I linearize this G mu nu, that is going to be 1/2 epsilon alpha beta mu nu times h alpha beta. So it's going to reproduce the linearized equation of motion for h mu nu by construction. Yeah.
Is the Einstein-Hilbert action uniquely fixed by the two conditions we have available?
Yes, up to boundary conditions.
So what would happen, for example, in modifications of GR where you add like higher powers of R?
Oh, sorry, no, it's not uniquely fixed. It's if you also require that you want the second order in an action which is second order in derivatives, then it is uniquely fixed. If you allow for more derivatives, then there will be additional terms that one cannot. However, those higher, they are called higher curvature corrections. So there are other terms that can be written added to this action which satisfy the first condition, because as we see, there are some objects that are we can consider scalars that are deep invariant, so those can be added here, and there are some of them that even start from cubic order, so they cannot even change what is the answer, or maybe at higher order, cubic or higher, and they cannot even change how the quadratic term looks like. So those, in principle, those are possibilities that can be added in this action. Those are not fixed by this requirement. However, these are called, in the usual language of particle physics, these are called irrelevant interactions, in the sense that if you are interested in low energy or large distance observables, like in gravity, we are talking about, I don't know, we are talking about a solar system or cosmology, these sort of things. As long as you are talking about large distance observables, those higher derivative terms are very negligible, or very small. Of course, they come with some scale, so that when they become important, it depends on the scale by which they appear. So for instance, let me just give you some concrete example. I can put something like R squared here. And then since R has 2 derivatives, this R squared has 4 derivatives. So if I want them to have the same dimension, I should put some energy scale here. So that's chi lambda. So there will be some scale, some energy scale, some length scale at which the corrections that are due to this term become important or relevant or observable. So if this lambda is very, very small, it would already be ruled out. So there are some observational constraints on the value of lambda, for instance, or the corresponding mass scales that suppress higher derivative, higher curvature corrections to this. It becomes a question of phenomenology. Yeah, there are a lot to it. But I can say that so far we haven't seen any deviation that requires us to add these terms. There hasn't been any experiment that tells us those terms have to be there, which means that the scale by which they are suppressed is very small. So for instance, if this lambda is the same as this, so for instance, if this lambda is of order of g, remember g is the dimension of 1 over length. So if lambda squared is of order of 1 over g, then distance become extremely small, and it's almost hopeless to see their contribution in any foreseeable future experiment. But you can imagine that lambda is larger than that, and then there might be some future experiments that are sensitive. So for the moment, we can forget about it. Or for this course, actually, we can forget. Other questions? Right, so by construction, this G mu nu, this Einstein tensor, when I linearize it, it gives me the linearized equation of motion for H mu nu. So what does it imply? It implies that I can do the following. So I can keep the linearized term here on the left-hand side and take the rest to the right-hand side. So let's write it as G1 mu nu equals 8 pi g T mu nu minus 1 over 8 pi g, or maybe plus 1 over 8 pi g minus g mu nu plus g1 mu nu. So I didn't do anything, I just added and subtracted this g1. I isolated this g1 mu nu. Now, the left-hand side of this equation is basically the linearized equation of HV nu that we had before. And as we showed, the property that it has is that the mu of G mu nu first order is equal to 0 because it's the mu nu of this operator and it is identically conserved. So this is 0, which means that this object that sits here, let me call it tau mu nu, that is also ordinarily conserved. So the way to think about this, so this part of it is T mu nu is this guy that supposed to be a nonlinear version of the matter stress energy tensor. We said that in the theory of gravity, we also have the contribution to a stress energy tensor that comes from the gravitational waves themselves. They also carry energy and momentum. So if we want to complete this linearized theory of gravity, not only that we need to put improve the matter stress energy tensor by including its interactions with gravity, we should put also the contribution of purely gravitational waves or gravitational fields. So we call that little t mu nu. So that's what one should think about this second term in here. The second term, one can think of it as a sum over contribution of the just purely gravitational contribution to the stress energy. So this is that's from n equals 2 to infinity, where n is the order in H mu nu.
I satisfy all the equation of motion order by order, first order, second order.
What do you mean all the equations?
No, order by order, first order, T mu nu.
You mean if you expand the equation of motion in parts of little h mu nu? Yeah, well, if I write some equation, something equal to 0, and then you expand it, it should be satisfied at all orders. But what I was saying was that what we saw was that if we take linearized theory for h mu nu, that satisfies the constraint. So whatever source that I put on the right-hand side of this equation should be compatible with this constraint. And that is very restrictive. It doesn't allow us to put an arbitrary source. The source has to satisfy this conservation condition. And that once you put T0 mu nu here, it uniquely fixes everything. You have to add higher order terms. And now what I'm saying is that this trick of constructing a covariant theory that automatically gives us that object that can see. So if we didn't come up with this trick to construct covariant theory, if we went on and just order by order improve the right-hand side of this equation, we would discover this action. But that would be a very painful way of getting this. Now, of course, this term that is written here is not is not a tensor. It's not a tensor on this general coordinate transformation. Simply because G1 mu nu is not a tensor. So T mu nu is a tensor, and this G mu nu is a tensor, but G1 mu nu is not. Therefore, this whole object, this whole tau mu nu is not a tensor. It's called a pseudo tensor. And it's easy to understand why there cannot be a tensor sitting here. It's because we, as we saw, we can have, once you have general covariance, once you have the choice of choosing different coordinate system, we can construct local inertial frames. And in local inertial frames, h mu nu is 0. Therefore, the stress energy tensor of gravitational part that can be set to 0 by going to one of these local inertial frames. However, if I have a tensor, then if all components of a tensor are 0 at a single point, they will be 0 in all other frames. Therefore, anything that is supposed to give us the stress energy tensor of the gravitational field, that cannot be a tensor. It is a pseudo tensor. But that's basically the best thing that we can come up with if we want to have some definition of energy in general relativity. So of course, when I talk about pseudo tensor, so usually in field theories we have this T mu nu that is supposed to give us the energy density. Here, this pseudo tensor is not uniquely defined, and therefore, like by going to different frames, I can get different answers for this pseudo tensor. I can shift the energy between different parts. But it's not even very well defined to talk about energy density. But one thing that it is useful for is to define the total energy and momentum in a space-time if I fix the asymptotic behavior. So remember, when we have charges, when we have conserved currents, we could define conserved charges by integrating them over the whole space. And those charges were conserved as long as there was no flux at infinity. So here, this tau mu nu is a pseudo tensor, but it's sufficiently good to give us conserved energy and momentum, conserved energy and momentum for the full space-time. If the space-time satisfies some nice asymptotic condition, which means that if at large distances it goes sufficiently fast to Minkowski space. So one can consider this object, this P mu nu, as the integral, this dx over some full time slice of this zeroth component of the pseudo tensor. And one can show that if the G mu nu, or let me say the other, if H mu nu as R goes to infinity, if H mu nu goes to 0, and actually if it goes to 0 fast enough, then this P mu is a 4 vector with respect to those asymptotic frame that my space-time approaches, and it is conserved. and it is independent of the choice of this slice that I choose. Similar to here. The argument is a bit complicated. You can still undo leaf sheets for the argument. But there is one relatively simple way to see why it should work. So that's what I'm going to say. But if you have questions, it's yeah.
So, well, what's the difference in the physical interpretation of T and tau?
T and tau.
Yes.
Well, it was something that was constructed just from the matter action. So if I set matter field to 0, if I set psi equal to 0, then T mu nu, this T mu nu becomes 0. While you can consider pure gravitational waves in the absence of matter field. So that carries some energy, and that would be inside the second part. So tau mu nu is the sum of the two.
So, in some books, I've also seen something called the Komar energy. Is it related to tau?
It's related to these asymptotic quantities that I'm going to define, or I define already. So so here this is a 4 vector that I define. Now you can imagine, so I'm considering some space-time which is asymptotically Minkowski, right? Now if this P mu that I define this way is time-like, then I can consider a boost with respect to this asymptotic frame, and so that this P mu becomes the spatial component becomes 0, so it just becomes P0 and then 0, 0, 0. And that object you can think of as the total mass in this space-time. No, there are different ways of calculating total mass in a space-time. There's Komar mass, there's ADM mass, there's Bondi mass, and depending on what configuration you are looking at, they might differ from one another. So the one that but in many configurations they actually agree. I think Komar mass and ADM mass I agree, as long as one talks about the static fields. This one that I define is the ADM mass, but it's definitely related to Komar. Okay, so how do we see that this object is how do we see that this object has some nice properties? Well, the conservation follows the usual arguments. Integrating some conserved quantity, some ordinarily conserved quantity, and that means that if I take time derivative of that is going to reduce to a surface term, and therefore it becomes 0. But of course the subtlety here is that we are talking about some curved space-time. So one can be worried about what's the meaning of this mu in this. Why is this object a Lorentz vector? Because even though asymptotically the space-time is Minkowski by assumption, inside there is going to be that metric, this h mu nu can be order 1 or large, so g mu nu can be very different from eta mu nu. And then we have freedom to choose different coordinate system. And in none of these coordinate systems, the spacetime is going to be Minkowski. Locally, it can be at some point, but at other points, it won't be necessary. So then the question is that what is the meaning of this mu index? Because this is, of course, a tensor index. When I go from one system of coordinates to the other, this tensor index changes. So the moment we don't have a global inertial frame, it's a bit ill-defined to sum up in the vectors that or tensors that sit at different points in a space-time. Okay, so the way to see why this object makes sense is to, for the moment, assume that it makes sense, and then use this equation. So this G1 mu nu, we said that it is conserved. It can actually be written as, so let me just raise one of the indices. So we are talking about G1 mu nu. And this can be written as the derivative of some other tensor. Again, it is linear. I don't write one, but this H alpha mu nu has the property that first of all it is first order in H mu nu, and secondly it has some explicit form, but I don't write it. It's written in the note. It is anti-symmetric with respect to these two indices. So this is equal to minus h mu alpha nu. Therefore, this makes it clear why, when I act by derivative with respect to mu, it has to vanish because of anti-symmetry. Because derivative is commute, but this is anti-symmetry in alpha mu. So it's if I take the alpha of h alpha mu, that is equal to 0. So it makes it automatic. Okay, so there is this, I can write this G1 mu nu in this form in terms of this other 3 index tensor. But it's not a real tensor again, it's just constructed out of one single h mu nu, so it is also a pseudo tensor. Once the right hand side is a pseudo tensor, the left hand side will also be a pseudo tensor. But okay, so let's use this Einstein equation to replace the pseudo tensor in terms of this other pseudo tensor. So we have the alpha of h alpha 0 mu, but since it is anti-symmetric and I chose 0 for one index, the other one should be a space index. So it becomes d3x di of h I0 mu.
Can you repeat that?
Repeat this one. Yeah, so what I did was there is tau mu nu here. If I use the Einstein equation, I can write tau mu nu as 1 over, so I missed 1 over 8 pi g. So I can write tau mu nu as 1 over 8 pi g times g1 mu nu, which is equal to 1 over 8 pi g Okay, so let me raise the index.
It's because antisymmetric. Okay.
I can write a 1 over 8 pi g d alpha this other object, and then I am just plugging this expression in here in my definition of p mu, right? So I get this, and so my p mu after I use this is going to reduce to this object. Yes, it is antisymmetric in I0. That's why for alpha I can only choose the spacing. Now, since it is a divergent, I can reduce this to a boundary term. So this becomes an integral over the boundary. Now, this P3x is supposed to be a full spatial hypersurface. But let's cut it off at some large radius and then send the radius to infinity. So this is a limit of r going to infinity, a surface element dsi times hi 0 mu.
This S is a two-dimensional hypersurface?
Yeah. So now this object, so by the way, this h mu, so G1 was second order derivative of h mu nu, right? It was something like D'Alembert to the different combination of two derivatives. But this h is it has one derivative of h mu nu. So like it has. Let me just randomly write one of the terms. So if you have a box here, then there has to be a term d alpha h mu nu, and then there will be other terms, and then there will be minus alpha exchange with mu, so that it becomes antisymmetric. So it's some object made of the first derivative of h mu nu. Now, this integral that we get here is very nice because it's an integral at very large distances where we say h mu nu is going to 0. So h mu nu is becoming small. When h mu nu is very small, we can go back to our linearized theory. We formulated the linearized theory as a theory of a tensor h mu nu that lives on Minkowski space. So remember, the starting point was just looking at the different degrees of freedom in Minkowski space. We were looking at the representation of Poincare symmetry, which was the symmetry of Minkowski space. So if I go at large distances and this property holds, when h mu nu becomes small, I get closer and closer to Minkowski. So now talking about now we can think of h mu nu as just some tensor field, some Lorentz tensor, not a tensor on the distance dimension, but a Lorentz tensor that lives in Minkowski space. And then we can use the usual arguments, the usual logic that we had before. Now, if I have a tensor that lives in a Lorentz tensor that lives in Minkowski, then it's well defined to add it up at different points. The same way that before, when we were not talking about gravity, we would talk about the total energy and total momentum in a process. So we would consider some scattering process or some decay process, and we would talk about some sum of pi equals sum of pf. I part of the in particles and f in the out particles. So as long as we are in Minkowski space, it's well defined to add, and these are 4 vectors. So it would be well defined to add 4 vectors at different points because we had some global frame, global inertial frame. So here is the same thing. As we go out to R to infinity, we have a global inertial frame, and this HI0 mu, it becomes a real 4 vector that can be added together. Its value at different points can be added together. Moreover, if this H has a component that goes as 1 over R, which does go to 0, then the derivative with a scale as 1 over R squared by this area element goes as R squared. So this full integral will have a finite limit. So we can get a finite limit for this integral, which is which is understandable why it is a 4 vector with respect to Lorentz transformations of that asymptotic inertial frame. Questions so far? Yes.
Why we doing this procedure, we're going to get like the full expression of G mu?
No, the full expression for G mu, we already know it. I have just not written it here, but so
why are we doing this thing of the field?
The moment I impose these 2 requirements, I fix this action. So this R is known. Once R is known, G mu is known. It's just the variation of this action with respect to G mu. So no, this we already know. I just don't write it here explicitly. If you like, I can, but it's just some messy expression in terms of Christoffel symbols and there. Why do we do this? Well, I wanted to talk about stress energy tensor and the concept of energy and momentum. So we are used to having or used to being able to talk about energy and momentum before considering gravity. In 5th years, we would talk about different processes that happen, and we would have conservation of energy and momentum before and after. The sum of the momenta before is equal to the sum of the momenta after. We had the concept of conserved energy momentum tensor that would give us some local density of energy and momentum, and once we would integrate it, it would give us the total energy and momentum. So we are doing this to understand if there is a generalization of that concept once we talk about the nonlinear theory of gravity.
So we're saying that if in first order it's the same, maybe in higher orders.
No, what I'm constructing is something that is supposed to be the full energy and momentum, not just the first order. I'm using these tricks to relate the full energy and momentum of the space-time to some integral taken over the first order. Well, to something that is related to h, just a linear expression in terms of asymptotic value of h mu and nu. But so if you go back here, this tau 0 mu is not a first order quantity. It's something that is supposed to be the full energy and momentum tensor. Well, it is not a tensor. It's just it's a pseudo tensor. But as I argued, there is no hope of getting a full tensor that has that has the meaning of energy momentum density and gives us the full energy momentum of the system.
So it doesn't matter if I don't have the full tensor, I can still define the conserved quantity in the usual way.
Yes, so I define this object, which is crucially, it is ordinarily conserved, not covariantly.
But that implies that a combination of T mu nu and G mu nu is the thing that is conserved. And the combination is the thing that asymptotically works like a vector. But it doesn't say anything about T mu nu and G mu nu. Like, we don't know if still is conserved or is that.
Oh, this property holds. This is always correct.
But the thing, T mu nu plus, the combination of T mu nu plus and G mu nu alone, are not. We don't
You
see.
mean this minus that, only this? That is zero. That's just the original equation.
But still we don't know what is conserved.
The zero is conserved.
It's conserved. So if it is conserved, when we are working in the first order correction and show that those are conserved.
Sorry, I don't know.
It would be better if we prove that the whole tensor is conserved, and then obviously the first and other orders may be conserved.
Yeah, I guess I still don't understand the question.
Why we don't explore or work out a bit at the G mu nu itself to see their properties instead of working with the properties of linear terms or first order terms?
Oh, the property of G mu nu. Yeah, maybe I didn't say something. That is. Let me tell you that. So you remember we showed that this holds as a condition, as a consequence of the fact that this matter action is invariant under diffeomorphism. So we showed that this is zero if I go on shell. Right? The same argument applied to the gravitational action implies that the G mu nu, this Einstein tensor is also conserved covariantly.
What is the geometric interpretation?
Sorry?
Geometric interpretation.
What is the
geometric interpretation?
The geometric interpretation of G mu nu?
And the fact that it's covering derivative.
Well, I haven't talked about geometry yet. We will talk about geometry later. At the moment, what I'm doing is that I'm considering some nonlinear theory for H mu nu. It's it's an interesting question to ask whether it has a geometric interpretation, and indeed it does have geometric interpretation. But from this perspective, it's just an interesting curiosity. I don't need to know the geometric interpretation of G mu nu to discuss energy and momentum.
So far, the G mu nu is just the...
It's just a nonlinear version of the equation, of motion for H mu nu.
We're having this Einstein action and working out the equation of motions and applying those constraints to... yeah. Okay.
Yeah, my goal here is just to construct a consistent nonlinear theory for gravity, for a spin 2 gravity. So what we saw was that the only way to construct a consistent nonlinear version of or linearized theory is to write this Einstein-Hilbert action plus a covariant matter action. And now, once we constructed this theory, the next question that I'm asking is that is there any notion of conserved energy and momentum in this nonlinear theory?
Okay.
So one thing that one can immediately see is that since this T mu nu is covariantly conserved and not ordinarily conserved, if you try to construct an object like d3x t0 mu out of this, that is not going to work as a conserved moment. And there is a very good reason for that, because you also have some energy in the gravitational field. This object vanishes when you set matter fields to 0, but obviously matter fields can give their energy to gravitational fields, so there cannot be conservation that is only based on this T mu nu. So therefore, we needed to add something that takes into account the energy stored in gravitational waves. We argued that that object cannot be an actual tensor. The best that we can hope for is something like a pseudo-tensor, and that is the pseudo-tensor that we came up with. So it is something that has the structure that we expect. It is ordinarily conserved. I can define this P mu, and then I can reduce it to a boundary term that shows why it makes sense to consider this, why I can think of it as a 4-vector assigned to the fuller space-time.
Okay. In practice, how would you calculate P mu?
In practice,
Given
like that.
Suppose.
I mean, that's one way, but I would say that's the easiest. It's like using Gauss's law to calculate the charge.
And to find H, you would have to linearize G for a general space-time, like a full metric. What do you linearize then?
Well, we assume that we are talking about asymptotically flat space. So imagine you have some curved space-time. I mean, the assumption is that you know the solution. So you know the solution, you know what is the metric in the full space-time. You know that asymptotically it becomes Minkowski. So you see how it approaches Minkowski. I can write this asymptotic metric in this form, and then this h mu by the assumption that it's gonna be asymptotically flat, h mu goes to 0. So I know how this h mu behaves. I derive that, I plug it in.
So to find h mu, so I don't have to assume in principle that h mu is small. Okay, just take the difference between the full metric and the Minkowski metric and linearizing whatever I get.
Mm-hmm.
Okay.
So the Sharping solution satisfy those conditions?
Yes.
So you should P0 should be the mass.
I cannot answer this question.
Okay.
Until next year.
So more or less we're showing that energy and momentum of gravitational waves are conserved.
No.
No.
Not gravitation. So this object, it contains the energy and momentum in the gravity plus matter.
But like
so the whole thing together is constant.
Like as above, like with the expression of the derivative of h alpha beta.
Really?
If you like, that does have contribution of gravitational waves.
But this is not Tom. I don't understand what you are asking. So this Tom mu has terms which correspond to the matter fields, and then this object which is quadratic and higher order in gravitational waves. Now I can relate the sum of these two to this object using the equations of motion.
But no, as above. Yeah.
Here. But this is not the energy momentum of gravitational waves. This is a linear expression.
You're like saying that. But again, that is also tau mu.
Yeah, using the equations of motion this time.
No, that is not that term.
This?
No. Epsilon alpha beta mu nu h alpha beta is not tau mu.
I mean, tau mu is this.
And that is that. So that is.
Well, I'm saying using the equations of motion, these two are equal to each other. Like you have some matter density, and then the equations are. So let me give you an example. In Maxwell theory, you have charge and you have electric field. The Maxwell equations relate charge to the electric field, right? Now in Maxwell theory, you ask what is the total amount of electric charge. There is a Gauss law that is derived from using Maxwell equation that relates the total amount of charge to the flux of the electric field. Is charge the same as electric field? These are related by the equations of motion, but this is a similar thing. There is something that I call a stress energy pseudotensor. And by the equation of motion, it's related to some field derivative, the second derivative of h mu nu field. Now I have derived an analog of a Gauss law that relates the total energy to the flux of this H field, which is first derivative of h mu nu.
So we're saying that And at the, I don't know, at Minkowski, the energy momentum of matter and gravitational field is conserved, and the momentum of the energy.
Yes, well, yes, that's exactly what we are saying. We are saying that if you calculate the total amount of energy, or in other words, maybe the better way of saying it is that if there is a way to define a conserved for momentum, if you have asymptotically Minkowski space. And that this is the way to define. So this is an object that is going to be conserved unless you have some fluxes to infinity. So as long as there is no flux of energy and momentum to infinity, this quantity is going to be conserved. Yeah.
The condition that I always have to have a asymptotic Minkowski space-time. I think so. Because
no, that's not the
criteria, because I know what happens there, right?
Yeah, so in principle, you can consider other situations. You always need some fixed,
something that I know.
Yeah, some fixed metric to compare things with respect to that. I mean, only in that situation you can hope for finding something. So, for instance, there are other examples of masses that are defined in, for instance, asymptotically untitled space-time.
Because what matters is the difference.
But what is crucial is that you have to nail the asymptotics of the space-time onto something that is predetermined and see how you deviate from that predetermined metric or predetermined space-time, and then tells you how much. Then you can hope that there might be some notion of mass that can be associated. More questions? Okay. I'm done for today. See you Friday.
No, Tuesday. Is it on Friday or Tuesday? Tomorrow.
What is
The last one, economical quantization.
three problems, right?
No.
Yeah, it's three problems.
Oh yes. The part.
He said only number one. We can let's question from the last one, right?
Yes, if you
Yes,
want.
because I took before was to take this.
He said the right
He said something about question 4. So
He said he would do it. We postponed the discussion.
I'm gonna ask him. Show you the reason? 4 hours is there. Yeah, I'm going right now.
Okay, so maybe tomorrow.
Okay, I'm going to the bar.
We're going to the library.
And you guys were alone?
We don't have a question.
I hate method.
What?
I hate method.
You kill me.
I hate method.
He hates me. Oh, you hate?
Yeah.
Okay, oh.
This is recorded, okay?
Yeah. But it's not bad. It's not bad to hate someone.
No,
I mean,
it's not bad. No, you don't.
Okay, let's change it.
Yeah.
No, I don't hate me. I just feel that I'm the dumbest guy.
No, I think I would love GR with someone with teaching with GR.
I start hating the subject, yes, but
I hate yeah.
I don't think I hate GR, it's
You
just
hit
how
anyone
we
in
teach
STP?
GR.
this is
Any professor?
I think it's not bad. I mean,
But I feel
I know
right now he's going on this.
slow in what?
Safe.
in my work
Ah,
there,
safe.
he's
Let him take his time. Because if you want to start doing the same thing as here, I'm done.
What I really like about that, if you ask him,
But sometimes, I mean, canonical quantization is getting just boring.
Mm.
20 years ago. Wow.